said, my name is Peter Schallenberger, and today I'm going to be talking about catalyst injection systems of polyethylene plants. Last summer I had the opportunity to work out at Westlake Chemical in Long Beach, Texas. I was a reliability engineering intern, which basically just means making sure that pumps, compressors, or any fixed equipment runs reliably over time. Just kind of predicting failures and making sure that if something breaks, we know when and why it might break. So a little introduction to polyethylene. It's a thermoplastic, which as you guys know just means that it can be reheated and cooled over and over again and it'll retain its original properties, whereas a thermoset, if you heat it up, it will basically change its chemical composition and will be a completely different substance. Polyethylene was first produced in the late 1890s by a German chemist on accident. It was produced at really high temperatures and pressures, and then in the early 1930s or late 1930s, early 1940s, they figured that by adding a catalyst, they could actually have that polymerization process occur at much lower temperatures and pressures, so it's much more producible on a large scale. So out at Westlake, they produce two types of polyethylene, LDPE and LLDPE. That's low density polyethylene and linear low density polyethylene. LDPE is made at low temperatures and pressures, and then LLDPE is made at high temperatures and pressures, nearly around 1,500 atts or 25,000 psi, so it's a very serious process if something goes wrong. I put on here two pictures. The first figure is just a wide range of products that LDPE is used in, and then on the right, this is where I knew it. Mostly from on the inside lining of these bags, there's actually a thin plastic film that Westlake provides a lot of the polyethylene for food grade safety and stuff like that. So this is a quick, just a process diagram of how polyethylene is made. On the left side, I showed you how ethylene turns into polyethylene within the reactor, and that's what's shown in the red box on the right. Inside that reactor, you have catalyst mixed with ethylene gas. It's a fluidized bed reactor, which if you guys have ever seen the videos of like sand with air coming up through the bottom, how it kind of floats around, that's the same idea inside the reactor. After that, it gets it's in a slurry form and it goes into a melt pump where additives are added into it, such as talc for like a no-slip feel or other additives depending on the customer. After that, it goes into an extruder, which turns it into a wax form, into a pelletizer, which goes into these titanium die plates. It's almost like a portafilter on an espresso machine, a bunch of really small holes. And then there's blades after that that'll cut it into pellets. It's cooled in cooling water, and then we transported it out by rail car. I'm going to be talking most about the catalyst and how it gets into the actual reactor at that really high pressure. So there's two stages of how that catalyst is actually pressurized and bumped up. Throughout the plant, you don't want to go from atmospheric to a super high pressure in one stage. It's really hard to do. So for the gas, the ethylene gas, we use multiple stages of compressors. For the catalyst, we use multiple stages of pumps. So the stage back from the reactor is actually the catalyst pump that you see here. The way that it works is through hydraulic intensification. It's really just a fancy way of saying if you provide the same force to that shaft with a large surface area on one side and a small surface area on the other, you're going to get a much higher pressure with the smaller surface area than with the larger one. So this catalyst pump is interesting in that it goes both ways, and there's check valves on each side that do that. So as you can see in this picture, as the actual piston is moving to the right, on the left side you will have the output closed, you'll have the suction open, so it's bringing in catalyst from the left, and then on the right side you will have the suction closed and the output open as it's exiting towards the reactor. Now this catalyst pump works by taking the hydraulic fluid pressurized up from the hydraulic pump and then pressurizing it up to the actual pressure needed in the reactor itself. So the hydraulic pump that I talked about before is going to take oil from about atmospheric pressure to a couple hundred psi, whereas the catalyst takes it from that couple hundred psi to 20,000 psi basically. And you may have seen these pictures before in system dynamics, but on the right it's a hydraulic pump that's an axial piston pump. And the way that it works is you have this swash plate that doesn't rotate, it's at an angle, but it can be altered depending on how much pressure you want and how much output of fluid that you want. And then the pistons will rotate around that swash plate. And as they reach the top part of the swash plate that's most angled back, they're the farthest away and they're actually sucking in that fluid. And then as it rotates towards the bottom, where it's much closer, it'll actually push that fluid out and bring it to the catalyst pump. Now what we saw in our plant a lot, we did a lot of older pumps that were actually had this pencil arm which controlled the swash plate. And when you try and get these pumps remade, the company doesn't want to do it because it's an obsolete version. So what they had is actually internal pressure controllers that could control the angle of the swash plate automatically without having to basically have input back to the operators and have them go and work on the actuator and try and deal with issues like that. Something that we also saw at the plant was issues with the connection between the motor and the pump itself. We had a lot of shaft failures and things like that, but what we didn't see was internal issues within the hydraulic pumps because they are pumping hydraulic fluid instead of some sort of process fluid, meaning that they are internally lubricated and don't have as many corrosion issues as other piping or pumps that are processing process fluid, whether it be catalyst or the actual polyethylene after. So just in conclusion, when you're pumping things in a plant process, usually there's a lot of different stages that you have to go through. Gas, you're going to deal a lot more with high power compressors, whereas liquids, it's a lot easier to just use these pumps. And the hydraulic pumps were great because they were internally lubricated, whereas the catalyst pumps, you have more issues because they were using both oil and the process